Hey guys, so we're going to look at this other paper. So this is science paper 1 GCE. Okay, so now we're going to start with section A, then we go in the same manner, just like that. So we look at section A. So section A, we have some questions here. So let's check out some questions we have in section A. So that's the first question in section A. So answer all the questions on the answer grid provided in the question paper. So we have the first question: which of the following is not an example of a basic unit? So one which is not an example, now it means three are examples of basic units. So one which is not an example of a basic unit here is actually the watt. So watt is not an example of a basic unit. There are actually about 7 fundamental quantities that we have, and amongst them wattage is not a part of them. Second is there coming from time, meter is there coming from length, ampere is there coming from current. So now we don't have watt on the basic units. So the answer is D. We proceed. We look at the other one. The following diagram shows a broken rule used to measure the length of an object. Okay, what is the zero error and the actual length of the object? So we start. So the zero error in this case is now look at what is happening. Initially this meter rule was supposed to start from the 0th centimeters, but it has started here. So the object, it is measuring actually from, so this is 3.8. so it has started from 3.8. So if you go like this is 4 coming down, this is 3.9, and this is 3.8. So meaning where this is starting from 3.8, so the zero error is 3.8. So now if 3.8 is the error, then what is the actual length? The actual length therefore is given by saying the final reading subtract the 0th error. So the final reading that we are seeing here is if you take here, this is 6, then it ended at 5.9. So the final reading is 5.9 if we subtract the 0th error, which was 3.8. So 5.9 subtract 3.8, we actually get 2.1 centimeters. So it simply means A is our answer for this one. Alright, we proceed. We look at another question. We go to question 3. A person dropped an orange from a basket on his head 1.8 meters to the ground. With what velocity does it take, or does it strike the ground? Alright, now with what velocity does it strike the ground? So now look at, a person dropped an orange. So we have this. So if you're dropping something that is actually coming down, okay, on his head, so the height was 1.8 meters to the ground, then with what velocity does it strike the ground? So we're actually looking for velocity here. Now velocity can be found in so we have this, we can say velocity is given by u plus at. So now from the 3 equations of motion, this is one of the equations that we can use to find velocity, where we have the initial velocity, we have the acceleration, and we have the time. Now from here they've just given us this is the height that we've been given. So we've been given height, then how do we find the final velocity? So to find the velocity on that end, velocity will be equal to, now I'm going to introduce a different formula. Now from those three equations of motion, we also have this one here where we say x is equal to ut plus half at squared. So we also have this one here which has a distance in it. So now how can you go about this? Then we have another one which has v squared is equal to u squared plus 2ax. So these are the ones that we have there. So now to find the final velocity, which one are we going to use? In here we have time. Do we have time? We are not given time. So basically I'm going to go with this one, the third one. So I'm going to say v squared. V squared is equal to the initial velocity. It started with was 0. So 0 squared plus 2. When coming down, the acceleration due to gravity is 10. Then the distance is 1.8. So they've given us a distance of 1.8. Then v squared is equal to 0 plus, here we have 10 times 1.8, which is 18. Then when you say 2 multiplied by 18, so we get 36. So we get 36 there. Then we're going to say v squared is equal to 36. Then when we square root that side, then our velocity will be equal to the square root of 36 is 6. Getting the positive value is 6 meters per second. So the velocity there is 6 meters per second, meaning our answer is choice C. Alright, we proceed. We look at another question, question F4. The following graph shows how the speed of a car varies with time. So what was happening to the motion of the car between 10 seconds and 20 seconds? So between 10 seconds and 20 seconds. Now look at 10 seconds is here and 20 seconds is there. So what was happening in between here? In between here. So in here, it means number one, the velocity was constant, but what was happening in terms of acceleration? There was no acceleration in here. So acceleration was 0. There was no acceleration there. So what we have, we are saying the acceleration of the car was 0. So D is the answer here. We look at another question, F5. A uniform plank is pivoted at its midpoint. 2 weights are added to the plank, 1 weight on each side of the pivot in the positions shown in the diagram. A vertical force is applied at an X to balance the plank. What is the size and direction of the force? So now this question is coming from moment, so you're supposed to be familiar with what we call the principle of moment. Now the principle of moment says that the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. Now let's look at this. We have a force here which is force X, so I'm going to do that. I'll say force 1 multiplied by distance 1. If we add it with, we have a second force here. So force 2 multiplied by the second distance, this should be equal to, we have another force, the third force, force 3 multiplied by the third distance, which is distance number 3. Then from there, we're going to say our first force is what? Is X. Then the distance from the pivot, so this is where the pivot is. So from here to there, we say 2 plus 2, which is 4. So we're going to have 4x here, then plus the second force is 12 multiplied by the second distance from here to there, it is 2, must be equal to the third force is 8 multiplied by the third distance from the pivot to there, that is 2. So this is the pivot is actually here, that's where the pivot is. So we have 4x there, 12 times 2 we get 24, then 8 times 2 we get 16. Then from there the 4x will remain. I'm going to say 16, 24 will cross the equal sign and it will be minus 24. Then 4x will be equal to, what is 16 minus 24? We get negative 8. Divide by 4, divide by 4. That goes, then x is equal to 4 into negative 8 is actually negative 2. Now, negative 2 newtons. Now we have found the force negative, and this should signal something to us. So it simply means the force was acting in the opposite direction. So it was acting upwards. No wonder it has become negative. If it was positive, it was supposed to be acting downwards. So it means the force is acting upwards. So we come there and we check. They're saying what is the size and direction of this force. The size of the force is 2 newtons. Then the negative shows us that it is acting upwards. So on 5, answer choice B is the correct one. We go to question 6. The following diagram shows a small pickup weighing 5,000 newtons approaching a hill. It moves up the hill at a constant speed. If the gravitational field strength is 10 newtons per kg, calculate the work done in moving the pickup the hill. Okay, so now we are looking for work done. Now, work done, remember, is given by force times distance. Now, the force, we have this one, which is 5,000 newtons. Then the distance, we've got two distances. We've got this and this. But in this case, always go by the vertical distance. So go by the vertical distance, which is 10. So when we say 5,000 times 10, you get your 50,000. So 50,000 joules. So 50,000 joules in standard form is the same as 5 times 10 to the power positive 4 joules. Or you can say 5.0. So you check what is there. So it means answer choice A is the correct option for question number 6. Therefore, proceed, move on to question A7. The following diagram shows a simple machine. Okay, what type of simple machine is it? Now, if you check the diagram again, it is a wheelbarrow. Now, a wheelbarrow is an example of a simple machine. So actually, there are certain simple machines that they can give you, and a wheelbarrow is an example of a particular type of a simple machine. All right, let me show you. So this is what we have here. This is what we have. So now this one is an example of a simple machine that we call a lever. So wheelbarrow is an example of a simple machine that we call a lever. Okay, we go to question 8. The following diagram shows boiling water and ice in a test tube. What is the aim of this experiment? Now look at what is happening here. We have a wire gauge here. We have ice cubes. Then you apply heat there. We have a test tube. Then boiling water. Now look at what is happening here. Water is able to boil, but whilst the ice cubes have not yet melted. So what is this experiment trying to show us? So this experiment is trying to show us that water is actually a bad conductor of heat. So water is a bad conductor of heat. So question 8, the answer choice should be D. Water is a bad conductor of heat. We proceed. We go to question A9. Which of the following equations best describes Charles' law of thermodynamics? So in short, we just want to find Charles' law. Okay, so in Charles' law, remember we've got this PV over T is equal to constant. So now, from here, from Charles' law, which one should be kept constant here? So PV over T is equal to K. So from Charles' law, which one should be kept constant? Which one should we remove between these three there? So this is actually a question on gas laws. So now, Charles' law, we have pressure that is actually kept constant. So in Charles' law, the pressure is kept constant. So for Charles' law, meaning if pressure is kept constant, we remain with V over T is equal to K. So pressure is kept constant. So you should also know the other laws. We have Boyle's law, we have Charles' law. So in Charles' law, pressure is kept constant. So this is the equation that would best describe Charles' law. So question 9, answer choice B is correct. We proceed to question 10. The following diagrams show thermometers used in a school laboratory. Which thermometer has the greatest range and which thermometer has the greatest sensitivity? So by range is just defined as the difference between the highest value and the lowest value. So like for instance, here the range from 0 to 20 is range here is 20. In here the range is 40. In here the range is 200. Then in this one is actually starting at 140 to 300. So we subtract 300, subtract 140, and we get 160. So the range is 160. So the one showing the greatest range here is this one. So V is showing the greatest range. Then which one has the greatest sensitivity? So by sensitivity, we mean which one is able to detect smaller temperatures. So that one should have smaller divisions. For instance, look at the first one, it's starting from 0 to 5 to 10. The second one from 0 to 30. The third one from 0 to 50. The fourth one, it is actually starting at 140. So meaning T is the one with the greatest sensitivity because it can actually detect smaller temperatures. It has smaller divisions. So our answer should contain V and T. So when we say greatest sensitivity should be T, then there should be V. So our answer choice should be B here. So the answer choice should be B there. Now proceed to another question. Okay, so we have question 11. So what question was that? So I think that was the answer to question what? Okay, so we have that. So the question we answered was question 10, I guess. Yes, that was question 10. So we go to question 11. So question 10 has been answered. We have question 11. Question 11, it is a wave of frequency 13,000 Hz travels 1,300 meters in 2 seconds. What is the wavelength of the wave? Now, there is what we call the wave equation, and the wave equation is such that we say V is equal to F times lambda. So it means the speed of a wave is equal to its frequency multiplied by its wavelength. So now the question is asking us to find the wavelength. So we say we make wavelength the subject to the formula here. That is gone, that is gone. Then wavelength will be equal to frequency, or I mean speed divided by frequency. Then frequency we've been given. The question is, have we been given speed? We've not, but we've been given distance and time, of which you know that speed can be calculated by saying distance over time, and the distance is 1300, then the time is 2. So 1300 divided by 2, so we can divide that so that we see what we're getting. So 1300 divided by 2, I'm getting 650. So 650 is my speed. So 650 divided by the frequency is 13,000. So if I say 650 divided by the frequency of 13,000, I'm actually getting 0.05 meters. So that is the wavelength. So I guess the answer here is answer choice A on question 11. Proceed. Look at another question, question 12. Light travels from air into a glass block of refractive index 1.5 as shown in the following diagram. Okay, calculate the diffraction, the angle of refraction in the glass block. So we have this. This is actually called an incident ray. Then the one coming out is called a refractive ray. So, and this line, the dotted line, is actually called the normal line. So this is referred to as the normal. So the angle between the normal line and the incident ray is actually called the angle of incidence. Then the angle between the normal and the diffractive ray is actually called the angle of diffraction. So how do you find the angle of diffraction given diffractive index and we've been given the angle of incidence? So we can actually use a law that we call Snell's law. So Snell's law will be helpful. So Snell's law states that the diffractive index is equal to the sine of the angle of incidence over the sine of the angle of refraction. The refractive index is 1.5, sine angle of incidence is 60, so sine 60 over sine angle of refraction we don't have, so we'll say over 1 and we cross multiply. So what we get? So I'll say 1.5 sine r is equal to sine 60 there. Then we're going to divide by 1.5. We divide by 1.5 there. That goes. Then sine r is equal to, we start by simplifying that. So what is sine 60? So we find sine 60, then we divide by that. So sine 60 divided by 1.5. Okay, I'm getting 0.577. So let me just write 0.57. Okay, 0.58 like that. Then to find r here, I'm going to say when sine crosses the cosine, it will be sine inverse of 0.58. So the angle of refraction will be the inverse of sine, then the answer we found. So I'm getting approximately 35 degrees. That's the answer I'm getting. So I'm going to check on the answer choices. If I have a 35, I actually have 35 on answer choice C. So choice C is the correct option here, 35 degrees. Now proceed. I look at question 13. A13. A person is standing 150 meters from the front of the cliff, claps his hands once and hears an echo after 0.9 seconds. Find the speed of sound in air. find the speed of sound in air. Now look at this. Suppose we have so a person standing from the front of the cliff. Okay, so let's say you've got a boundary here and the person is there. So if a person is to clap, sound will go like that in that direction, then it will come back as an echo. So now the time it takes, it's saying it will take 0.9 seconds. Then if it goes, so if it goes going, the distance is 150 meters. So the distance is 150 meters and coming back again is 150 meters. So how do we find speed? So speed will be equal to distance over time. Now in this case it will be speed is equal to 2 distance over time. Why? Because it is going and coming back. So 2 times 150 divided by time, which is 0.9 seconds. So 2 times 150 is 300 divided by time, which is 0.9. So what we get when we say 300 divided by 0.9, we get 33. We get 333.33. So I'm getting 333.3 recurring like that. So meters per second. So meaning our answer is answer choice D. So D is final answer. Go to question 14. Which of the following does loudness of sound depend on? So loudness of sound actually depends on what we call amplitude. So that is where loudness of sound depends on. Okay, question 15. The following diagrams show a small compass close to a strong bar magnet. Which diagram shows the correct compass direction? So now look at, so here, so we have a small compass and that is close to a strong bar magnet. So we have answer choice A, B, C or D. Then want to find out what is going to happen. So in short, what is the direction of the compass? Now remember, one thing you should note is that when magnetic field lines, suppose this is south, this is north, magnetic field lines always move from north to south. So they move from north to south. So now the direction of the field line, they are not supposed to move inside in this direction or that direction or that direction. They are actually supposed to move away from the north like that. So the direction in here, it's supposed to go away from the north. So it's supposed to point away from the north. So answer choice D is correct. That's the answer for number 15. We go to question 16. A negatively charged rod is held close to but not touching an insulated metal sphere as shown in the diagram. We have a charged rod, then we have a metal sphere here which is neutral, so meaning it has an equal amount of positive and negative charges. Which diagram shows the correct charge distribution on the sphere? Now what will happen here is that when introduced a negatively charged rod, all the positives inside this sphere will come and align themselves near the negative. It will come and attract the positives, then it will repel the negatives on the other hand. So meaning we're supposed to look for a diagram that is similar to the one that we've just shown, and the diagram that is similar to the one we've just shown is diagram B. So B is the answer for question 16. Go to question 17. Which of the following circuit diagrams shows all the three resistors in parallel? So the one which is showing all the three resistors in parallel, it is choice D. So choice D is showing all the three resistors in parallel. We go to question 18. An ideal transformer has an input voltage of 12 volts and an output voltage of 240 volts. It has 2000 turns in the primary coil. Find the number of turns in the secondary coil. Right. So now, in order for us to find the number of turns in the secondary coil, we're going to use what we call the transformer equation. The transformer equation is such that it states that the primary voltage divided by the secondary voltage should be equal to number of turns in the primary coil divided by number of turns in the secondary coil. So here, the word input mostly goes with primary and output goes with secondary. So input voltage of 12 volts. So primary volt, we're going to say 12. Secondary voltage, we're going to say 240 volts. The number of turns in the primary, they've given us 2000 turns. The number of turns in the secondary coil, we don't have. So cross multiply, then we have 12 multiplied by number of turns in the secondary, then this will be 240 multiplied by 2000 divided by 12. Even here we're going to divide by 12. That will go. Number of turns in the secondary will be equal to, we first multiply what is on top, that is 240 multiplied by 2000, then we divide by 12. So we're getting about 40,000. So we're getting 40,000. So the number of turns in the secondary is 40,000 turns. We go to question 18, or question 19 I mean. Which of the following radioactive emissions has the strongest ionizing effect? Now, the one with the strongest ionizing effect is an alpha radiation. So, it is an alpha. So, an alpha has got the strongest ionizing effect. It's an alpha. Question 20, which is the last question on the multiple choice section. So, last question on the multiple choice section, question 20. So we're going to look at it. We see how best we can go about it. So there is our question 20. Radium has a half-life of 1600 years. Calculate the number of half-lives it will undergo for 100 grams mass to reduce to 12.5 grams. So this is what we have. We have 100 grams. Now this should reduce to about 12.5 grams. So what are we going to do? So in fact, let me do that. Okay. So we're saying this should reduce to 12.5 grams. So now we're saying when after 1600 years it will reduce to 50 grams. Again, after another 1600 years it will reduce to half of 50, which is 25. Then again, after 1600 years it will reduce to half of 25, which is 12.5. So meaning we have 1, 2, 3. You just count the number of arrows. So meaning 3 half-lives. So we have 3 half-lives that are going to that it's going to take. Okay, so we are done with section A. We now proceed to section B. We look at questions in section B. Section B has got 9 questions. Question B1 up to B9. So let us start from B1 and see how best we can tackle the questions. Okay, so let me start with the first one. So that's the question. Figure B1.1 shows a simple pendulum suspended on a clamp stand for determining the periodic time. Okay. First question, what is meant by periodic time of a simple pendulum? Alright, so periodic time of a simple pendulum is the time taken for a pendulum bob to complete one oscillation. So the definition is the time taken for a pendulum bob to complete one oscillation. So that is what is meant by periodic time of a simple pendulum. Then state two factors that do not affect the period of a pendulum. So two factors that do not affect the period of the pendulum, we have mass of the bob, it doesn't affect. Then we also have the shape of the bob, this also doesn't affect. So you can say mass and shape of the bob. So these, they do not affect the period of a pendulum. Alright, we proceed. Question C. This experiment is done on Earth and repeated on the Moon. Where would the periodic time be higher? So is it on Moon or Earth? So the answer here is on the Moon. So we say on the Moon. Then the question is why? Justify your answer. Why are we saying on the Moon? So we are saying on the Moon because the gravitational field strength is less on the Moon as compared to Earth. So the G on the Moon is less than the G on the Earth is more. So the lesser the gravitational field strength, the higher the periodic time of the pendulum. So that is how it is. So the lesser the gravitational strength, the higher the periodic time. Alright, we proceed. We look at another question. We have question B2. Figure B2.1 shows an apparatus a learner used to measure the mass of an irregular object. Take G to be 10 newtons per kg. Right. So from there now, so we actually have a balance, a beam balance, that is measuring the mass of an irregular solid. The first question is, what is the weight of the irregular solid? Okay, so basically weight is measured as a formula. Weight is equal to mg, mass times gravity, where mass should be in kilograms. So our mass is 350 grams. You just convert this one to kilograms by dividing it by 1000. So 350 divided by 1000. So what do we get? We get 0.35 kilograms. So weight will be equal to mass is 0.35 kilograms multiplied by acceleration due to gravity. They've given us 10 newtons per kg. So the kilogram will go, 0.35 multiplied by 10, we get 3.5 newtons. So 3.5 newtons is our answer here. We proceed. We look at part B. The learner measured the weight of an object on top of Mount Everest and also down the same mountain using a spring balance. So here we're looking at weight. What was his observation about the two weights? Now, suppose this is what we have. So we have an object on Mount Everest and the same object is measured down here. So what do you think will be an observation between the two? So one observation, observation that would make between the two is that the weight of the object will be greater down and less on the mountain. So we can just simply say the weight. So we can say the weight was more down the mountain. So the weight was more down the mountain. So if the weight was more down the mountain, we know it was less on top of the mountain. So give a reason for the learner's observation. Why are we saying that? So we are simply saying that because we are looking at the value of G. So the value of G on top will be less compared to down. So the value of G down will be more than on top. So we are saying the value of the gravitational field strength, which is G, is more on F. So which is just down. So is more. So we're looking at it down the mountain. So is more down the mountain. So it is more down the mountain. Alright, so that is the answer. We proceed, we look at another question. So we have question B3. Figure B3.1 shows the graph of a car that moved from a residential area into town. Then describe the motion of the car from AB, BC, and CD. So AB, BC, and CD. How can we describe the motion of the car? So between point A and B, what do you think was happening? So between point A and B, what do you think was happening? So there was constant acceleration. So constant acceleration. So the acceleration was constant. Then between point B and C, there was zero acceleration. Between point C and D, there was constant deceleration. So there was constant deceleration. So we can mention it in terms of acceleration or in terms of velocity. So in terms of velocity, between A and B, there was uniform increasing velocity. So you can also do it in terms of velocity, but I prefer, for now, I'd go by acceleration. So between point A and B, the acceleration was constant. Between B and C, there was zero acceleration. Between C and D, it was constant deceleration because the graph was going down, the velocity was decreasing. Right, so meaning you've described that. It's 1 mark for each description. What was the acceleration when the car was moving with a constant velocity? So when the car was moving with a constant velocity, the acceleration is 0. So the acceleration is 0 meters per second squared. So constant velocity means 0 acceleration. Okay, proceed. Question B4, figure B4.1 shows a seesaw balanced with forces as indicated. So we have some explanations there. They want us to, number one, state the principle of moment. So I'll state it. The principle of moment states that for a body in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. For a body in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. That is what principle of moment states. Then they want us to calculate the distance y. The distance y. So we go and check where is our distance y. So on B, they want us to calculate the distance y. Okay, so that is what they want us to do. So okay, so our distance y, how do we calculate? So we're going to calculate our distance y by using the principle of moment. So remember, we were going to start, so the first force multiplied by the first distance should be equal to the second force multiplied by the second distance plus, so since these two forces are on the other side, on the same side, so we're going to say, no wonder we are adding them, the third force multiplied by the third distance. So the first force is 200 newtons. First distance from the pivot, this is where the pivot is, 2 meters, should be equal to, the second force is 150. The second distance from the pivot is y. So we have y there, plus the third force is 110. Then the third distance is 2 meters, that one from the pivot. 200 times 2 is 400. 150 times y is 150y. 110 times 2 is 220. 220 to cross the equal sign so that it becomes 400. Subtract 220. So this is going to give us 150y. 400 subtract 220. What do we get? So we simply get 180. So 180 is equal to 150y, divide by 150, divide by 150, that is gone, that is gone. Then y will be equal to, what is 180 divided by 150? So we get 1.2 meters. 1.2 meters. So the value of y on B, so what we've answered here is the answer for question B. Y is 1.2 meters. We go back, we check, that's the distance. Then we go to C, find the force X acting upwards at the pivot. So let's check force X acting upwards on the pivot. Acting upwards. Alright. So let us look at this. This is force X. This is force X. Now, force X, which is acting upwards, is as a result of the forces which are acting downwards. So, the forces which are acting downwards should be equal to the force which is acting upwards. So now, this force which is acting upwards should be as a result of the summation of all the forces which are acting downwards. So what I mean is, to find force X, you should add all the forces that you see. We have 200 newtons, we have 150 newtons, we have 110 newtons. 200 plus 150 is 350, 350 plus 110 is 460 newtons. So that one is the force acting upward. So that is force X. That is how you can find that one. Okay. Proceed. We look at another question. So this was a question on principle of moment. So we will look at another question now. We have question B5. An 8 kilogram brick fell from a building under construction. The brick fell from a height of 80 meters. Take G to be 10 newtons per kg. The first question, calculate the potential energy. Now, how do we find potential energy? It's easier. Potential energy, so we'll do that. Potential energy is given by mgh. Potential energy is equal to, where m is a mass, the mass is 8 kg. So 8, the mass should be in kg. The gravity, they've given us 10 newtons per kg. The height should be meters, which is 80 meters. So when you multiply 8 times 10, that's 80. Then when you say 80 multiplied by 80, so that one should give us about 6,400. So 6,400 joules. So that is the potential energy. So now that potential energy has been found, they're saying calculate the potential energy after falling halfway down. So potential energy after falling halfway down will be equal to the total potential energy divided by 2. So the total potential energy was 6,400. We divide it by 2 so that we get 3,200 joules. So this is halfway. So that one is halfway. Then part B, calculate the kinetic energy of the brick after falling for 3 seconds. Now kinetic energy is given by half then mv squared. Do we have the mass? We have. Do we have the velocity? We don't have velocity. How do we find velocity? Velocity is equal to u plus at. Now the initial velocity is 0, then the acceleration due to gravity is 10, then our time is 3 seconds. So 0 plus 10 times 3 is 30, then 0 plus 30, that is 30 meters per second. That is our velocity. So I'll say half our mass. If you take on top, our mass was 8 kilograms. Our V is 30, then it is squared. Half of 8 is 4 multiplied by 30 squared. What do we get when we say 4 multiplied by 30 squared? We should get 3,600 joules. So that one should be our kinetic energy. That is how you can go about that one. We proceed. We look at B6. B6 part A. What is boiling? So I'll just give you the definition of boiling. Boiling is defined as the change of state from liquid to gas at a particular temperature. I repeat, boiling is defined as the change of state from liquid to gas at a particular temperature. As simple as that. Second question, state 2 factors that affect the boiling point of a liquid. So the boiling point of a liquid is affected by what we call number 1, purity, then number 2, pressure. So those are the 2 factors that affect boiling of a liquid. But C, explain 2 differences between boiling and evaporation. The first difference is that in boiling there are bubbles. So in boiling there bubbles are seen, but in evaporation there are no bubbles. That's the first difference. Second difference that you can put there is that boiling occurs at a specific temperature. So temperature for boiling is specific. So boiling occurs at a specific temperature. But what of evaporation? Evaporation occurs at any temperature. So that's also one other major difference. Alright, so you just write them properly, then you get the answers. We proceed. We go to question B7. Figure B7.1 shows the brightness of the electromagnetic radiation with different wavelengths. So we have that. What's the question? From the graph, determine the wavelength where the radiation is brightest. So let's check. Radiation is brightest where? Actually it's here, that's why it's brightest. So you just come down. That's why this is why it's brightest. So I'll just come down and check the wavelength down. It's here. If this is 1.0, this will be 1.1. then this will be 1.2. So I have 1.2 times 10 to the power negative 6. The power of 10 will maintain. The power of 10 will maintain. So I have 1.2 times 10 to the power negative 6. What are the units? Meters. That one has been found. If the wavelength of visible light rays are between 4.0 times 10 to the power negative 7 meters and 7.0 times 10 to the power negative 7 meters, what is the name of the radiation in A above? So the name of the radiation in A above. Now for this one, I think you're supposed to be familiar with all the electromagnetic radiations. Yeah, if you're familiar with all those, you'll be able to know their powers of 10, like in terms of wavelength, their powers of 10 and how they follow each other. So like which one follows visible light, which one is below it, which one is above it. So there is a table of all those electromagnetic radiations. You're supposed to be familiar with it, know their powers of 10 in terms of wavelength or frequency. So but for this one, the answer is ultraviolet. So for that one, the answer is ultraviolet. So ultraviolet is the answer. UV light. Okay, we go to part C. Calculate the frequency of the radiation in part A. Now remember, in part A we found the wavelength to be 1.2 times 10 to the power negative 6 meters. So how do we find frequency? Frequency is given by the speed divided by wavelength. So speed, they have given us that. So speed is 3 times 10 to the power 8. Then the wavelength is 1.2 times 10 to the power negative 6. So if you divide these two, you should get 2.5 times 10 to the power 14 hertz. So 2.5 times 10 to the power 14 hertz. Alright, proceed. We look at state 1 use of radiation in A. So we said what type of radiation is that? Ultraviolet. Now one use of ultraviolet is to create what we call to create fluorescent. So to create fluorescent. That's one use of that. Now there are many uses that you can put, such as in phototherapy and also in killing bacteria, but you can just go for one. Only one was needed. Alright, we proceed. We go to question B8. Figure B8.1 shows bar magnets with different poles. Identify the following poles: P, R, T, then and Y. Okay, P, R, T, Y. So one thing you should know here is the magnetic field lines, they always move from the North Pole to the South Pole. So they move from north to south, never from south to north. So it's from north to south. So meaning, look at the arrows, they are moving from Q to P. So meaning Q here is north, P is south. So I know that P is the South Pole. Then if Q is north, an opposite pole will come here, which is south. So I know that R is also south. Alright. Then I proceed. I say, look at V. It is coming from the north, going where V is. So look at the arrows, they're going where V is. They're going where V is. So this simply means V is south, then T must be north. So T is north. If T is north, Y, they're coming from Y. Again, Y is north. Y is north. then W will be south. So that is how you can put that. Here you just needed to know to say magnetic field lines, they move from north to south. As simple as that. Figure B 9.1 shows a circuit consisting of a 12 volts battery with a combination of resistors between points X, Y and Z. Alright. Then what is the question asking us to find? First one, calculate the effective resistors between Y and Z in the circuit. So effective resistors between Y and Z. Now look at Y and Z. These resistors, they are in what? They are in parallel. So resistors in parallel, total resistors in parallel is given by resistor 1 times resistor 2, you multiply them, then you add them down. So on top you multiply. So if I say this is my first R1, this is my R2, so I'll say 6 multiplied by 12 divided by 6 plus 12. So once you do that, you are going to find 4 ohms. Going to find 4 ohms as your resistors between Y and Z. So this is my answer for question A. Then I proceed, I look at B, find the current passing, or find the current through the 2 ohms resistor. Find the current through the 2 ohms resistor. So the current through the 2 ohms resistor. So I need to find the total resistance. Since I've already found these resistors in parallel, then with this it has now become a series. So to find the resistors, I'll just say resistor 1 plus resistor 2, where we have got 2 plus here we have found 4. So altogether we have 6 ohms. Then we proceed now. How do you find current? They're asking us to find current. That is part B. Current is equal to voltage over resistance. The voltage, we already have voltage here, 12 volts. Resistors, we found 6. 6 into 12 is 2 amps. So the current is 2 amps. So current has been found. We proceed, we look at another question. Calculate the voltage across the 2 ohms resistor. So voltage across the 2 ohms resistor. So that is for part C. How do we find voltage? Voltage is equal to current times resistors. Then the current, we've already found 2 amps. So we'll say 2. Then the resistors, they've given us 2 ohms. So 2 multiplied by 2, we have 4 volts. So 4 volts, that is the answer that we have found for this one. So that one has been dealt with. Now proceed to another question. We are done with section B. We now go to section C. Answer any 2 questions from this section in the separate answer booklet provided. Elena carried out a Hooke's law experiment using standard 50 grams masses and obtained the following results as shown in table C1.1. So this is a table. Complete the table C1.1 for the values of the load N and extension. So we just want to complete the table. So how do we complete the table there? So let us complete the table. Look at, we have that. So we have mass, then we're looking for load. Now load is just simply weight. Now remember, weight is equal to mass in kilograms times gravity. So what we do basically is that this is 50 grams. You convert it to kilograms by dividing by 1000. So I'll say 50 grams, or divide it by 1000 so that it becomes a kilogram. So 50 divided by 1000, I get 0.05. So now this 0.05 that I found, is in kg. So 0.05. This is the one that I'll multiply with the acceleration due to gravity, and I'll get 0.5. So I'll put 0.5 here. You do the same for all. So you convert them to kilograms, then you multiply them by 10. So you find 0.5 here, you find 1.0 here, you find 1.5 here, you find 2.0 here, you find 2.5 here, you find 3.0 here, you find 3.5. You get a 1 mark for that one. You come to extension. From 10 to 12, what's the difference? The difference is 2.0. From 10 to 14, the difference is 4. From 10 to 16, the difference is 6. From 10 to 18, the difference is 8. From 10 to 19.5, the difference is 9.5. From 10 to 20.5, the difference is 10.5. From 10 to 21.0, the difference is 11.0. So extension, you just get where 10 was initially the length of a spring. So as you are loading, it is increasing. So we just needed to get the difference between the length of the extension when it was not loaded with the length of the extension when it has different forces. So meaning you get 2 marks for doing that. Then you proceed to the other question. Use the values obtained in A to plot a graph of extension against load. So plotting a graph of extension against load. So basically what you can do is you can plot. Right, so what I'll do is I'll just give you direction. So you draw the axis, the y and the x, then you can give it a title. Ensure that you give your graph a title. You can say the title is extension versus load. So you say extension versus load in full. So extension versus load. Then what you can do is you can come up with now using an actual graph paper that you have, you look at what we have here. So what we are doing is we are looking at what we have here. So on the vertical one, what are we going to put? On the vertical one, we are putting extension, since we are saying extension versus load. So vertically, we are putting extension, then horizontally, we are putting load. Then the load is going up to 3.5. So I can say this is 1, this is 2, this is 3, this is 4. Then the extension is going up to 11. So the extension is going up to 11. Okay, so I can say if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it is going up to 11. Then I can start loading. So where I know to say if load was the load was 0.0, the extension was also 0.0. So it will actually start from the 0.0 position here. You start from here. When load was 0.5, extension was 2.0. When load was 0.5, extension was 2.0. So you start plotting from there. When load was 1.0, extension was 4.0. Okay, 1,4 there. Then basically what it's supposed to do is you plot 6,1.5. So you go where 6 is. When the load was 1.5, extension went to 6. So 1.5 extension went to 6, just like that. So you're going to discover that at the end of the day, you should have something like that. So something like that when you plot O. So you plot O, then you should have something that will move in such a manner, like that. So that is what we are supposed to have. Similarly, then after you are done doing that, after you are done plotting, so meaning you've plotted a graph of extension against load, then on your graph show the elastic limit. So how do you show the elastic limit? So the elastic limit, you look at the point where it was moving straight, then it turns. So the point of elasticity will be a point. So in my diagram, so where it was turning from, in my diagram, this will become the elastic limit. So on your graph, you're supposed to check on the point where it no longer became a straight line, where it started bending. That is the point where the elastic limit is. That is the point where the elastic limit is. Okay? From the graph, show the load N when the extension was 9.0. So what you do is you go where 9.0 is. I'll give you an example. 1, 2, 3, 4, 5, 6, 7, 8, 9. You locate where 9.0 is. Then after you locate where 9.0 is, you follow the graph like that. After you follow it, you come, you bring it down there, then you check the load which is there. Then the load which is there is the one that you get. Yeah, so the load from there, that is you check, let's see, that is D. Okay, so what are we going to find there? So you check, you should get about the load, you should get about 2.5. So somewhere between, so it's not supposed, here it's showing above 2.5, but you should get somewhere 2.5. So on D, you should get about 2.5. Should get somewhere 2.5 newtons. Then state the condition under which Hooke's law is obeyed. State the conditions under which Hooke's law is obeyed. So the condition under which Hooke's law should be obeyed is that the elastic limit should never be exceeded. So elastic limit should not be exceeded. So elastic limit should not be exceeded. Should not be exceeded. So the elastic limit should not be exceeded. So that is the condition under which Hooke's law should be obeyed. So meaning that question is done, we go to the other question, which is question C2. During an experiment, a learner used a liquid in glass thermometer to check on how heat was affecting the temperature of water. Table C2.1 shows temperatures of water at specified times. What is temperature? Just a definition. Temperature is defined as, how can we define temperature? In simplicity, temperature is defined as the measure of coldness or hotness of a substance. The measure of coldness or hotness of a substance. As simple as that. Then plot a graph of temperature against time. So using a graph paper, but I'm just going to do a sketch. Just going to do a sketch of the graph of temperature against time. So I'll just do a sketch there so that you'll be able to follow. So you give it a title. Give it a title to say temperature versus time. Okay. So you look at what we have here. So we have time and we have temperature. So automatically time will come here. So time is seconds. So time is the one that will come down. Then temperature temperature will go on the other end. So temperature will go this side here. Then we need to balance. So we have temperature from okay, we have time from 0. Let me start with time. Time is starting from 0 all the way to 360. So how can we space that? So it depends with your graph. How can you space that one out? So you can say, if you want, you can say maybe from here to there I'll get a 60. Then from here to there I'll get a 120. From here to there I'll get a 180. From here to there I'll get a 240, then to 300, then to 360. So you can space it. You can leave a difference of 60. It depends with your graph. But if you want, you can leave 40. It depends with your graph. Then from there you can now space out the temperature. So how best can I space out the temperature? So I can say, okay, we have 21 all the way going up to what? So the temperature is going up to 53. So the temperature is going up to 53. So how best can I go about with the temperature? So I'll say, so let's say we have 21, 27, 32, that all the way up to 53. So I can space it here depending with the graph and what you have. So I'll say if I have 10, 20, 30, 40. So let's say if I say this is my 10, this is my 20, this is my 30, this is my 40, this is my 50, this is my 60. So I can say, let me space it with intervals of 10. So with intervals of 10, then you plot. So when time was 0, temperature was 21.5. So you go where 21.5, maybe somewhere here. When time was 60, temperature was 27, somewhere 27.0. So 27.0, maybe somewhere there. When time was 120, temperature was 32, somewhere there. When time was 180, temperature was 37, somewhere there. When time was 240, temperature was 40. So what I'm saying here is that at the end of the day, we are going to have a straight line. We're going to have a straight line that will move like that. So we're going to have a straight line in that direction. So that is what we're going to have. Then you just ensure that you plot, you space it very well. Then after you plot, then use the graph to determine the temperature of water at 210 seconds. So to determine the temperature of water at 210 seconds, so what you do is that you go where 210. So if this is me, this is 240. So maybe 210 will be somewhere here. So I'll go on top and meet my graph like that. Then I'll turn and check for the temperature that is there. So I'll check for the temperature that is there. Then I write the temperature that I'm going to find. So now basically there I'm not going to find, I'm supposed to check on my graph. Okay, so I check on my graph. Okay, so now it depends with how, so this one is not well, I've not labeled it very well, but with me you can see it is above, somewhere above 45. So maybe 46 or 47. That is what I'm finding, but so this is not accurate. So meaning you can try to do yours and see what you're going to find. So because basically they are going to follow your graph, how it's going to come out and how you're going to go about it with everything. So with me, I'm finding above 45, but I'm sure you should your answer should just be somewhere maybe 40 or maybe less than 40, so by maybe 39, somewhere there. So those are the ranges you're supposed to find your answer. So me, I'll leave it here. Then from there, it was observed that 75 degrees Celsius, the temperature of water stopped rising while the supply of heat continued. So we are saying the temperature of water stopped rising, but the supply of heat continued. So why do you think that happened? Why do you think that happened? So the reason why that happened, now I want to explain the observation. It is because the water was changing from liquid to gas. So when the water was changing from liquid to gas, there was a constant temperature. So the temperature stopped rising. So because the water was changing from liquid to gas. Okay, if the liquid used for the above experiment was pure water, state why it boiled at 75 degrees Celsius. So now remember, at some point we looked at the factors that affect boiling. So factors that affect boiling, one of them we looked at purity. If the water is pure, the other factor that is going to affect is pressure. So we're going to say this is because the atmospheric pressure was reduced. So if pressure is reduced, water is going to boil at a lower temperature as compared to the temperature that it was supposed to boil at. So this is because atmospheric pressure was reduced. Alright. Then the other question, suggest a liquid that would have been used in a glass thermometer for the experiment. A liquid that would have been used is mercury. So a liquid would have been used is mercury. So that is how best you can go about it. Then from there, now we go to question C3. Figure C 3.1 below shows a decay curve for iodine 131. Okay, we have iodine 131, so we have a decay curve of iodine 131. What was the original mass of the sample? What was the original mass of the sample? Now look at that one. The original mass of the sample, so it started from here, then it was decaying. So this is where it started from. So the original mass of the sample is 200. The mass is in kilograms, is 200 kilograms. So that is the original mass of the sample. So you answer that one. Then what is the half-life of the sample? So to find the half-life, you look at half of the mass. So this is one, then the second one. To find half-life, we get half of that, which is what is half of 200? Half of 200 is 100. So you go where there is half of the mass. So where 100 is, then you go and touch the graph, then you follow it down. Now go and check the time you're going to find there. So the time is somewhere between 8 and 12. So somewhere between 8 and 12, I would say 10. So time is in days, so I would say 10 days. That is just an approximate. Maybe it might be 11, maybe it might be 9, but 10 days is okay. So 10 days is okay. Let us look at another one. What quantity of the sample had remained after 24 days? What quantity of the sample had remained after 24 days? Okay, now let us look at the quantity. After 24 days, after 24 days, look at this is 24. This is 24. So after 24 days, you do this, then you follow this now. You follow this now. Follow this. So after 24 days, so we have something that is slightly, so something that is somewhere there. So what can we say this is? So I think this is about, this is somewhere 20, 19, 18, somewhere there. So if I find this one, so I would say I'll give a guess where it's an approximate. So the quantity that had remained after 24 days, I would say 19 kilograms. 19 kilograms. Yes, that would be my approximate guess that I would give. Then if the sample decayed by emitting gamma rays and an alpha particle to produce a new element X, write an equation for the decay. Write an equation for the decay. So how do we write the decay equation? So that is what we're going to do. So it is emitting gamma and an alpha particle to produce element X. So let us write the decay equation. So let's see. They gave us iodine. So iodine, so I'll say I for iodine. So it is having 131, then it is having 53 down. So when this one decays, we're saying it is supposed to give us element X. So it's supposed to give us element X, of which the element X, we don't know the mass and atomic number. So element X, then what else? So when that one decays, it's supposed to give an alpha and a gamma. So an alpha is actually defined as a helium nuclei. An alpha particle is defined as a helium nuclei. Then it will also give a gamma particle. Now gamma, it is just like that. So now how do we find that one now? So we're going to say, what is 131 subtract 4, because we want to balance what is on top. 131 subtract 4, that is 127. 127 subtract 0, that is still 127. 53 subtract 2, that is 51. So we have 51 here. So that is what we have. So basically this is the decay equation that we can write, or we can just write it as we have that 131, we have 53, so that one is going to give us X. 127 here, 51, then plus an alpha. If you want, we can do that. That is an alpha particle, a helium nuclei. So that is our decay equation. So that is our decay equation. Okay. From there now we look at another question. Okay. Give two properties of each of the following. So now we have gamma rays. So what are the properties of gamma rays? So if we are to give two properties of gamma rays, so the first property of gamma rays is that it doesn't have a mass. So they don't have a mass. So no mass. Then the other property of gamma rays is that they've got a high penetration power. So apart from not having mass, they've got a high penetrating power. So they've got a very high penetrating power. So those are the two you can put. Now what of alpha particles? So alpha particles, number one, we can say they are positively charged. Positively charged. That's one of the properties. The other property that you can put for alpha particles is that they've got this one had a high, they've got a low penetrating power. So we've got a low penetrating power, just like that. Okay, then mention one use of gamma rays. So one use of gamma rays is in the treatment of cancer. So one use of a gamma rays is in the treatment of cancer. So that is the one important use of gamma rays. So we are done. So pass through this and let me know where you are going to have challenges. Thank you.